Hey guys, welcome back to Cougar Chem Tutoring. I'm Austin, and I'll be running through an Exam 3 review for Chem 105. This will run through topics between kinetic molecular theory and heat work and energy, and you'll see kind of the topics. I'll be including timestamps so that you know what topics specifically we'll be covering here, and so you can jump to the ones that you want. But for right now, as far as fall 2021 goes, this exam review will be most accurate up till fall 2021. I can't guarantee that for future classes, but if you look at any of the videos I have or any of the other reviews I have, I also have timestamps, and you're welcome to look through those for specific topics that you'd like to review, okay? All right, so the first concept that we'll be covering is a concept within the realm of kinetic molecular theory known as root mean square speed. Okay, so root mean square is another statistical variable that we use in statistics. It's not really common in especially basic statistics, but when we're looking at gas samples, we actually use this a lot. So this is the gas particles over here. When we're looking at gas samples, hopefully you know that the mode is the most common variable. The median is the most center value, and then the mean is the average value, okay? And within a right skew distribution like this is kind of where you would see this, okay? In a perfect distribution, the mode, median, and mean would actually hopefully be all the same. But in this case, since we're all right skewed on most of these, it's going to be like that. So in the root mean square speed is kind of another one of these variables. Quite frankly, you don't really need to know where it is. It's probably going to be somewhere within this range here, okay? But what it is it's gonna indicate, all you need to know for the test is that it indicates the speed of the particle that has the average kinetic energy of the whole gas sample, okay? Mathematically, we actually write it like this. Oops. It's going to be the URMS, so that's just RMS speed, is equal to the square root of 3RT over mass. Okay, so 3RT, 3R is just the constants, the R constant, and then T is temperature in Kelvin, and M is molar mass in kilograms per mole. Okay, this RMS speed, the higher the temperature, the higher the RMS speed. The higher the mass, the lower the RMS speed. Okay, so when you're looking at a distribution of gases like this, when you're trying to figure out which curve would represent a particular gas, what I would do first is assume that they're at the same temperature and look at their molar masses. So I would just say, okay, I know that that's 32, that's 18, that's about 4, that's 2, and that's 14, or that's let's say 28. Sorry, 28. Okay. And if I know these molar masses, knowing that they're in the same temperature, the only thing that will differentiate them is their molar masses. Now, the heavier the gas, the slower it moves, right? Mathematically, that's how we figured out. But also intuitively, you could probably think, okay, if it's something that's heavier, it's a lot harder for it to move faster, okay? So in this case, what we're going to look for is the curves that represent certain root mean square speeds and rank them based on molecular weights of these gases. So the narrower the curve, the heavier the gas. And the reason is because that means on this red curve here, we would actually assume that the root mean square speed is somewhere like right there. But on this orange curve, it's like way out here. So the more broad you get, the further out the root mean square speed velocity gets, and the further in you get, the further in it also gets. Okay, so in this case, the heavier the gas, the narrower the curve, meaning the further left it's going to be. So I'm going to probably assume that this is O2 because it's the heaviest of all of these, and then probably N2 because it's the next heaviest, and then so on and so forth, just ranking these based off their weights. So probably H2O here, HE, and then H2, okay? And we could double check our answers. I have the answers listed here, but you can kind of see that this will always follow a pattern of weight, okay? Typically, a graph like this will always assume that they're at the same temperature, okay? And that there's 1 mole of each thing. So in this case, there would be 1 mole of this guy, 1 mole of this guy, 1 mole of this guy. They wouldn't really give you a different number of moles, and they also wouldn't put this at a different temperature. They would say, okay, this is all at 25 degrees Celsius. And something important to note is a question like this may come up, and it's really important to know the difference. It says, which gas has the highest amount of kinetic energy if this distribution is done at 20 degrees Celsius? Okay. So if these gas samples are done at 20 degrees Celsius, it doesn't matter what the gas is, the kinetic energy will be the same. Now, the distribution of speeds may be different, and that's only because their molecular weights differ, right? But if you look at the RMS equation, right, this is 3RT over M. Even if all of them have the same T, you'll notice that the molar masses can differ, can change the RMS speed, and by extension, the distribution of speeds. So what you have to know is that any gas that is at the same temperature here is what's representing kinetic energy. Any gas that is at the same temperature as another gas will have the same kinetic energy, but they may have a different distribution of speeds. In fact, they most likely will have a different distribution of speeds because they will likely have different masses. If by some random chance they were at both the same temperature and had the same mass, they would technically have both the same kinetic energy and the same distribution of speeds. But that's really rare because most molar masses of compounds will differ, even if it's just slightly by a little bit. All right, so I hope that kind of makes sense and that kind of gives you an idea of what RMS speeds are. In terms of kinetic molecular theory, there's one other question that we'll cover here later in the review that you'll need to know. But for the most part, what we've covered and the question later that we'll cover will pretty much sum up the way that they'll ask you questions about RMS. If you can kind of go backwards and forwards with them a little bit, kind of know the ins and outs of them, you'll be able to answer any question that they give you related to kinetic molecular theory. Another concept they'll test you on is the ideal gas law. Okay, a question may ask you something like this. A gas at STP increases 3 times its volume, and the temperature raises to 357 Kelvin. What is the new pressure? Okay, so now we have a condition 1. I'm going to put condition 1 over here, and a condition 2, right? We're saying that something changed to make condition 1 look different from condition 2. A gas at STP, hopefully you know that this is standard temperature and pressure. For this case, that would mean that temperature is 273 Kelvin and that pressure is 1 atmosphere. Okay, that is standard temperature and pressure for the ideal gas law. STP, in other concepts related to chemistry, will actually have a different temperature. Typically, the pressure will still be 1 atmosphere, but the temperature will differ. But just know that it's going to be 273 for this question. Okay, and then they tell us that from this condition, that the volume changed, increased 3 times its original volume, that the temperature increased, and so they're asking us what happened to the next one. So in this case, what I'm going to do then is I'm going to show you a way to solve this that I think makes it a lot simpler. If you write the ideal gas law, which hopefully you know, if not, it's on your equation sheet, but it's just helpful to know also off the top of your head. If you put an X above everything that is changing, and then move it algebraically to one side, what you end up doing is, in this case, I know that pressure, volume, and temperature are all changing. You're setting it equal to a constant. Okay, this is constant, and that must be equal to, or that must also be equal to a second condition using the same variables. Okay, so if I call this condition 1 over here and this condition 2 over here, and they're both equal to the same thing because the moles didn't change and the R constant stays the same, then I can technically set them equal to each other. So I say P1 V1 over T1 is equal to P2 V2 over T2. All right. And in this case, they're asking what the new pressure is. In that case, the variable I'm looking for is P2, right? So algebraically, I'm just going to solve for P2 first. So I'm going to put T2 up here. That'll cancel that down here, and V2 down here, which will cancel that right there. So ultimately, P2 is equal to P1 times V1 times T2 over T1 V2, all right? And in the first case, they told us that there's 1 atmosphere. And that in this case, they didn't tell us the volume, the actual volume, but we can just assume that it's 1 because the ratio of the first condition to the second condition will just stay the same no matter what number you put in there. It's going to be a 1-to-3 ratio. So even if I can even just put 1 liter if I wanted to, it doesn't even matter what the unit is because as long as it's 3 times more, it really doesn't matter. T2, we ended up at what? 357 Kelvin. And then that's divided by the first condition, which we said was 273 Kelvin. And then the V2, remember, it increased 3 times its volume, and we said that the first one is 1 liter, so let's just say the second one is 3 liters. All right, so once you do that, if you calculate that all out, you end up getting 0.436 using sig figs, okay? And what would that be? That would be an answer of atmospheres. So does it make sense? Let's see if it makes sense conceptually why the original pressure would decrease, right? It was at 1 atmosphere and it decreased to 0.436 atmospheres. Well, the volume increased. When volume increases, right, PV have inverse relationships. So let's say PV was equal to 1. Okay, if volume goes up, then pressure goes down. Let's say volume went up to 2, then pressure had to go down 1/2, okay? And so they have this inverse relationship. So when the volume increased, I would expect that the pressure would decrease. And that's what I see in this answer numerically. As well as the temperature raising. Well, the temperature raising actually kind of brings it up because they have a direct relationship, right? So when P goes up, or when T goes up, P has to go up as well in order to equal the same thing. So In this case, what I would say is that somehow, even though the temperature was raised, the factor of the volume changing by so much had a more of effect on the pressure than the temperature because it decreased so much, okay? Also, one thing I want to make sure I made clear, when you're looking at this equation and you know you're going to have these two conditions like this, it's really easy to do what I just showed you here, where you have one condition, set it equal to a constant, and then set it equal to second conditions, and that'll make the math really easy to think about. If you know that, let's say in the Pivnert equation, that all four variables other than the R constant are changing, then you can manipulate this. It doesn't necessarily have to match any law that you know. Whoops, this is N and this is R. But as long as you can set it equal to some constant, it's going to come out with the ratios and the equations that you need. So it's not going to match, you know, let's say it doesn't match one of the laws perfectly, like PV is equal to PV. It doesn't have to, as long as you know what's changing and they can manipulate this equation and then set it equal to the constants and then the second condition, okay? All right, so also on ideal gas law, you may have a question that's something like this. If a balloon has 1 liter of gas and you want to increase it by 10 times its volume, how many liters of the gas will you need to add? Now, you may ask yourself, why is he including such an easy question on this review? Because there may be a question where you're like, okay, yeah, I need to increase it by 10 times its value, so that means I need a 10-liter balloon, so I'm going to add 10 liters into this balloon. But what you forgot is that, well, not necessarily you, but what some students forget is that that's not how much they have to add. That's where you're ending at. You have to add 9 liters in order to get from the 1 liter to the 10 liter, which is 10 times its value, right? So be wary of this, okay? This is not necessarily, I didn't include this to go through a bunch of math with you. I included this mostly because there may be a trick question that's something like, okay, you know that you want to get to this point. How much would you have to add? You have to remember that you already have some, that you're adding to it, and that you're not multiplying by a simple number and then just using the final value. All right, for the next problem, you're still going to be using the ideal gas law, but you're going to actually, it's easier if you use a derivation of the ideal gas law. So it says if you have 10.257 grams of a 5.56 liter balloon at a pressure of 805 torr and a temperature of 28 degrees Celsius, what is the molar mass of the gas? Okay, so hopefully you remember that molar mass is equal to grams per mole, right? And I'm going to say grams is a little m as in mass, and moles is n as in moles, okay? Like the n that we use in the Pivnert equation. So if I look at the Pivnert equation, the ideal gas law equation, if I look at this n is technically equal to what? Little m over big M, because big M is equal to little m over little n, right? If I just flip these guys and solve for n, I can get little m in mass, which is grams, over big M, which is grams per mole. And then I can technically plug this in for n here. When I do that, I get the following. Little m over big M, RT, okay? And if I solve for big M, because they want the molar mass, right, and this is molar mass down here, I can actually solve for this, multiply this over, and then get these guys down here. That ends up looking like this. Molar mass is equal to little m, RT, over PV. Okay, and at this point, it's just straight algebra, except for, you know, changing some of the units of the pressure and volume. But other than that, I mean, this is how you would solve for this. So mass in this case is going to be, what, 10.257 grams, which is what they gave us. The R constant, remember that you're using the R constant for liter atmospheres, okay, not joules per mole Kelvin. So in this case, in order to do that, you have to use the 0.082057 liter atmospheres, okay, per mole Kelvin. You have to use that one because we have PV in here. That ends up being a liter atmosphere, which is a unit of energy, actually, and it can be converted into joules. But if you use the wrong R constant, you'll actually use the joules per mole Kelvin, which is 8.314, and you'd end up getting the problem wrong. And they will definitely have an option on the questions that will have the answer that if you had done everything right and just used the wrong R constant, that you would get this answer and it would be wrong. So just be wary of that. Make sure you're using the right R constant when you're using the ideal gas law. Okay, and then the temperature here, they give it to us in Celsius, but the R constant is in Kelvin, and so we have to put our temperature in Kelvin. When we do that, we get 301 Kelvin, more or less. Okay, and then that's going to be over, and then the pressure here, they gave it to us in torr. The R constant is in liter atmospheres, so in order to cancel out the atmospheres, I have to put the pressure in atmospheres, so that would be 805 torr. Hopefully you know that there are 760 torr in 1 atmosphere, and when you get that out, you get about 1.06 atmospheres. So I'm going to plug that in here, 1.06 atmospheres. And then lastly, our volume, they actually give it to us in the unit that we need, so we don't need to change anything. That's going to be 5.56 liters. And that way my liters cancel here, my atmospheres cancel there, my Kelvin cancel here, and then I get an answer that's in grams per mole. Okay, and when you do that all correctly, you should get about, it'll be around 43 grams per mole. Okay. I'm not going to be too exact with the number here, but as long as you got around this ballpark, you'll know that you did it correctly. Okay, so my suggestion is to solve everything symbolically first, algebraically manipulating the variables so that you have the one that you're looking for on one side and all the other ones on the other side, and then just plug in the values and make sure that you're using the right units, right? For this equation, you have to have it in an atmosphere, you have to have it in Kelvin, otherwise it's not going to come out the right answer, okay? All right, so another type of question they could ask you is in relation to how many protons or how many subatomic particles are in a given gas sample given certain numbers, okay? So it says if you have a balloon filled with helium, if you have a balloon filled with helium with a volume of 5.67 liters at STP, how many protons are in the balloon? Okay, so hopefully one thing that you can figure out without having to know anything else really is that looking at the periodic table, that one helium atom has 2 protons. Okay, so if you know that, okay, if you can go from there. If you know how many helium atoms you have, you can figure out how many protons you have. And in order to figure out how many atoms you have to have moles so that you can use Avogadro's number to go from moles to atoms. Now the question is, can you go from liters to moles? And the answer is yes, because at STP, you have to have this memorized. This is not on your equation sheet. At STP, 1 mole of any gas, 1 mole of gas X is what I'll say, is equal to 22.4 liters, okay? At STP. This is only at STP. So at STP, if they give you some volume of some gas, so you know how many moles there are if you use the dimensional analysis correctly. So in this case, I have 5.67 liters of helium gas, and then I know that if there's one mole of helium in 22.4 liters of helium gas. So now I've figured out how many moles of helium I have, and we know how to go from moles to atoms. We just use Avogadro's number. So that's 1 mole of helium. It's going to be 6.022 times 10 to the 23. That would be helium atoms, right? That's 1 mole. And then I know that in 1 helium atom, there are 2 protons. Okay, and at this point, you just multiply everything on the top and divide by everything on the bottom. And if you do that correctly, you end up getting about 3.05 times 10 to the 23, and that would be protons. Okay, so hopefully you haven't forgotten anything about unit dimensional analysis from the beginning of the semester. We are still using it, but also hopefully you knew that at STP, 1 mole of any gas is equal to 22.4 liters of that gas. So the next 2 questions we'll be cover the kinetic molecular theory, which is what we were covering previous to the ideal gas law here. It's another version of what they may ask you regarding speeds, okay? So this one says, if gas X moves 7 times faster than gas Y, what is the relationship between their masses? The equation that you need to know is what we call Graham's law. The URMS speed of one gas, we'll say this is gas X, compared to the URMS speed of another gas, which we'll say is Y, is equal to the square root of the inverse of their molar masses. So in this case, it would be mass Y over the molar mass of gas X. Okay. Now what they've said is that this speed is 7 times faster than this speed. So I'm going to set this equal to 7 over 1, right? Because this is as if this was 7 and this was 1 down here. So when I set this equal to 7, I can square both sides. Whoops. I can square both sides. And if I do that, I can solve for m over y over m over x. My over m over mx, and that's equal to 49. Now, if in terms of the relationship between their masses, that would just mean that my is 49 times bigger than mass x. So that would be my answer. My is 49 times bigger or heavier than the mass of x. Okay, that would be the answer for something like this. Now, another way they could do it is they may give you the masses here and ask you how the speeds are related, or vice versa. So, but as long as you know this equation right here, where it's speed of gas A over speed of gas B is equal to square root of mass of B over mass of A, that's all you need to know. And it's just a derivation of the RMS speed equation where we have 3RT over m. All we're doing here is we're relating, if this is gas A, we're just putting it over 3RT over mB. And in this case, they end up canceling, and the square root will stay, but the 3RT all cancels because those will all be constant, and then that's how we end up getting this equation. Another way they may ask you a question, or another question they may ask you regarding the RMS speed is what affects the RMS speed? And you just really have to know this equation, and it will tell you everything for this, something like this. So it says, of the following, determine which will affect the RMS speed of a particle. Here's a hint. If it's not in the equation, it's not going to affect the RMS speed. Even if you're thinking, oh, well, what about the ideal gas law? If P goes up, then T goes up. And if T goes up, then RMS speed goes up. And that's not how it works, okay? So volume is not going to affect it simply because it's not a variable in here. So I'm going to cross that out. Temperature definitely does, right? It is clearly right here. The reason it does is because it has temperature is what determines kinetic energy. And the average kinetic energy is what determines your RMS speed. So it has a direct effect on it. Pressure does not have a direct effect on the RMS speed of the particle. Molar mass definitely does, right? It's right here in the equation. Number of moles of gas does not matter either, okay? And the presence of another gas in the sample will also not affect it. So just know that the only variables will be temperature and molar mass, because those are the only varying types of variables in the equation. The other ones are constants, right? 3 and R, those are both, they're always going to be the same. So temperature and molar mass are the only things that affect an RMS speed of a particle. Don't get tripped up by other questions that said, oh yeah, we added argon gas into this, so what would be the new RMS speed? Don't be tricked by that, okay? All right, now we're moving on to a totally new concept known as intermolecular forces, okay? These are intermolecular forces, IM forces for short. Now, in order to answer a question like this, you have to know all the possible intermolecular forces. And what do they mean by dominant? That means there are intermolecular forces that are stronger than others. So you should know these levels of intermolecular forces. Going from weakest to strongest, we have London dispersion, dipole-induced dipole, dipole-dipole, hydrogen bonds, ion dipole, and then ionic. Okay, those 6 you should have memorized, or at least be able to understand conceptually and recognize them in a problem. So one thing I'd like to cover is what the principle behind London dispersion, because all molecules, whether they're polar, nonpolar, or even ionic, have London dispersion forces. So if they ever ask, what are all the possible intermolecular forces, and it's some polar substance, you know that at least it has London dispersion, and because it's polar, it would be dipole-dipole. So London dispersion is in everything. Now, let's say I had a given pentane molecule. Pentane has its own electron cloud that surrounds it. And let's say it got close to another pentane, okay? It's interacting with itself. When electron clouds, remember, electrons are negatively charged. When electron clouds get close to one another, they repel each other because they're the same charge, right? So when this gets close to this cloud gets close to this cloud, it repels one of the other clouds. So I'm going to draw the other. Here's the other second situation. It's still, this one's still normal, but now this electron cloud, this pentane, now has the electron cloud shifted down like this. Okay. And what that does is it creates a delta positive and a delta negative, where there's extra electrons on this side, so we call it a partial negative, and there's deficiency in this side, so we call it a partial positive. Now, the negative charge on these electrons here on this electron cloud are attracted to this now delta positive, right? The nuclei on this substance right here are a little bit more exposed because the electrons have been shifted towards the other side. And so this electron cloud will interact with this delta positive, and that is the principle behind a London dispersion force. And you will see similar principles that dictate how these the intermolecular forces work in both dipole-induced dipole, dipole-dipole, and hydrogen bonds, and other types of interactions, okay? So if you can understand this concept, you'll be able to understand most of how everything else works. So, knowing that London dispersion occurs in all molecules, if you have 2 nonpolar substances, those are typically the only. That's typically going to be the only type of intermolecular force present, because they're not going to have dipoles, so they're not going to have dipole-dipole. They can't have hydrogen bonds, because hydrogen bonds, I'll talk about in a second, are pretty much just dipole-dipoles on steroids, and so they're not going to have be present in nonpolar substances either. So London dispersions are typically really involved with two nonpolar substances, or a nonpolar substance that's just interacting with itself. Okay. All right. Now, dipole-induced dipole is the next strongest intermolecular force that you can have. Now, but just given its name, this is something that has a dipole, which means it's polar. Okay, and something that didn't originally have a dipole, but had one induced into it, like we did here. Such as in a nonpolar substance. So let's say I take something like water, which is very polar. Okay, if I were to draw its electron cloud, remember oxygen's very electronegative, so the electron cloud's kind of shifted towards oxygen like this. Okay, where we have a delta negative and a delta positive on this side. Now, if this delta negative gets close to, let's say, another pentane, a nonpolar substance, okay? It can repel this electron cloud one way. And so we see the same situation here, except now instead of repelling electron clouds, where it's still electrons repelling, it's just that we have an extra delta negative repelling the electron cloud, which shifts the electron cloud of pentane further. And that creates another delta positive, which is strong and interacts with that delta negative from the polar substance. So that's a dipole-induced dipole, meaning this originally didn't have a dipole, but the polar substance induced that dipole into it and then interacted with the dipole that it just created. So that's always between a polar and a nonpolar substance. This is one of the few where they would have to give you two different substances in order to have an answer for dipole-induced dipole. They couldn't just tell you H2O and then and then have that as the answer, because this would have to be interacting with some other substance that's not a polar substance. It would have to be nonpolar. So that'll happen with cases with number 2, dipole-induced dipole, and ion dipole. Okay, and I've noted that down here just in case you want some clarification. All right, dipole-dipole is just what it says. It's a dipole interacting with a dipole, meaning a polar substance interacting with another polar substance. So that's like water's delta negative here interacting with another water's delta positive. Okay, so let's say I have that. I've got the delta positive down here. That will interact with this guy, and that's the positive-negative interaction that will create this intermolecular force. And that's going to be polar substances, so things that have dipoles in them. Now, the next level, a steroid version of dipole-dipole interactions, are what we call hydrogen bonds. Hydrogen bonds are defined by having an H or a hydrogen bound to either H or N, O, or F, and then it's interacting with another N, O, or F. Now, the reason that this is so powerful, and it's even stronger than a regular dipole-dipole, is because the electronegativity values of the N, O, and F are very high. And so the dipole is extremely strong. It's extra strong than a regular dipole. Okay, it's not just an unequal distribution. It's like a super unequal distribution of electrons. Okay, it's no longer equal. So anytime you have H bound to N, O, or F, okay, and it's interacting with another N, O, or F, that is a very strong dipole, and it will be a hydrogen bond. And the reason they call it a hydrogen bond and not just a hydrogen interaction is because it actually functions as a bond sometimes. It's actually, these bonds are actually what hold our DNA together. And that's why they kind of call them bonds, because it kind of stabilizes things. So even though they're not actual bonds like we've talked about in ionic and covalent, it kind of functions at it because it's so strong. All right, next strongest one is an ion dipole. It's just exactly what it says, something that's ionic, whether it's cation or anion, meaning positive or negatively charged, interacting with a dipole, meaning it's a positively charged substance. So that would be something like if we dissolved, let me go ahead and erase these. Let's say we dissolved a salt in water. NaCl, right? NaCl splits up in Na plus and Cl minus in water, and the reason is because when an Na plus and a Cl minus, they're originally ionically bound to each other, but they fall into this river of oxygen or of water molecules. Okay, when I draw this, just know that this is oxygen and these are two hydrogens. Okay, and that's just how I'm going to draw water. Okay, so when I have this little Mickey Mouse here, this end here is the delta positive, and this here is the delta negative. And this delta negative will surround, there will be a bunch of little water molecules that surround these guys, to the point where the sum total of all the delta negatives from this water will actually overcome the full negative charge coming from the chlorine and separate them. And that's why things dissolve, ionic substances dissolve. And it would look exactly the opposite here because the delta positive is on the hydrogen end. It would look like that. So that is a typical ion-dipole interaction where you have, something that's charged like Na plus or Cl minus interacting with a polar substance like water that has a delta plus and a delta minus end. And that's a very typical example is dissolving. Last one is ionic. This one's actually also a typical bond intramolecular force, but it actually functions as an intermolecular force as well, because you can have Na plus, NaCl, right? Let's say I have Na and Cl right here. This Na, let's say it's ionically bound to this Cl. It can technically also be bound to another Cl over here. And if you called this a unit, this would be an intermolecular force because it's one unit of molecule interacting with another. But really, they're kind of the same thing, and you'll notice that they kind of function as the same thing. So just know that these 6 right here, if you can understand these and recognize them when they're given to you on a problem, it's really easy. Now, when they say the dominant intermolecular force, what they're really saying is name the highest or the strongest of this level. So let's say, take water, for example, again. Water has a dipole, right? We know it has a dipole, but it also has a hydrogen bond, right? There's our HO, and it's interacting with another HO. So it has this, and it has this, but it's also, as all molecules do, it also has London dispersion forces. So technically, if they were to ask you what intermolecular forces does water have, you would say hydrogen bonds, dipole-dipole, and London dispersion. But in this case, when they're asking for the dominant intermolecular force, you would say hydrogen bonds because that is the strongest of the three. So in the problem that they've asked us about, they've actually asked us about which one is the dominant intermolecular force, right? The most powerful. So what we have to do is pretty much figure out what the nature of each substance is, and based off that, figure out what the intermolecular force is. So if I look at this one, this is going to be barium fluoride. Now, if you look at where barium is on the periodic table, barium is in the second group on the periodic table, and it's a metal. Okay, that's an alkaline earth metal. And it's combining with fluorine, which is a non-metal, okay? And that creates ionic bonds, if you remember that from earlier in the semester. When a metal plus a non-metal come together, they create an ionic bond, which means I'm going to assume that this is a cation binding to an anion. And if I were to look at what charge barium has, barium is in the second group, so I'm going to assume it has a 2+ charge. And fluorine is going to have a 1- because it's one short of the octet, so it'll take on 1 electron. And when they come together, can you see why they come together in this ratio? That's why it becomes BAF2 to become neutralized. So ultimately, this is going to be ionic, both as a bond, but also as an intermolecular force, because ionic is also considered an intermolecular force. All right, letter B. On the rest of these, I'm going to have to draw some Lewis structures and explain some shapes. And these are things that you should have already covered and hopefully mastered by this point. So I'm not going to cover too much in how I get these. I'm just going to cover why they're either polar or nonpolar or etc. Okay. So in this case, I get bromine, and I got a fluorine here on top. And then I'm going to draw this in somewhat in the 3D just so this makes sense a little bit. Okay, so remember, dashes are going into the page, and then these wedges here are coming out of the page. It's our way of trying to draw in 3D. It's not great, but it's what we can use. All right, and then bromine has this lone pair. Now this lone pair is on the plane of the page. It's going down, and when I look at this shape, this is what we called square pyramidal. Okay, it's because it looks like a pyramid with a square base. Okay, and that's because it's got this lone pair on the bottom that's preventing it from looking like an octahedron. Okay. And what happens is when you have a dipole in bonds, which in this case they do, because the difference in electronegativity between bromine and fluorine is both greater than 0.5 and less than 0.2, okay? Whoops, less than 0.2, okay? Pretty much anything bound to fluorine is going to be polar, because polar has such a strong electronegative value that it just pulls so much. So each of these has a dipole. And remember, in a molecule can be polar if and only if, one, there are polar bonds, which in this case we do have polar bonds, and there is asymmetry, meaning there's an unequal distribution of vectors of dipoles. Now, let me show you what I mean. So I'm going to go back a little bit so I can kind of use this shape a little bit more. So what's happening is there's a vector going straight up. There's a vector going to the back here, up here, and out this way. Okay. Now these vectors are right directly across from each other, and they cancel out because they're in the same direction and magnitude opposite of one another. Okay. Same with these guys. These guys cancel. They're in the same plane, and they're with the same magnitude and directions in opposite directions, and so they immediately cancel in one another. But this vector right here is not canceled by anybody, and so there's an overall dipole going upward. Now, the vector, when I'm referring to vector, I'm referring to the vector of the dipole, the magnitude and direction of a dipole. So there's an uncanceled vector, which makes this polar, which is why most molecules that have lone pairs are polar, because the lone pairs will create an area where it's not canceling out a vector or a dipole. And so because this is polar, I'm going to assume that when they list it by itself, that it's interacting with itself. And so a dipole with another dipole would just be dipole. Okay, I'm just going to put dip just for short, just to keep it short. All right, does that make sense? Let's go. Hopefully, if it doesn't make sense, I'm hoping that it'll make more sense once we cover these other ones. Okay, so CH3OH, that's just, that's just carbon with a hydrogen, and then an OH over here. Okay, remember OH, that should be key for saying, oh, okay, that must be a hydrogen bond. Okay, that's a hydrogen bond because hydrogen is bound to O, or N or F, in this case it's just O, and it can hydrogen bond with another O from another CH3OH. Okay, So when it's interacting with itself, I'm assuming that this is the hydrogen bond right there, okay? So I'm going to put hydrogen bond. It technically also has dipole-dipole, right? But it's not the most dominant intermolecular force. We're looking for the dominant intermolecular force. Okay, if you look at INCL, there may be different values that you look up, but if you look at the electronegativity values, these will be slightly, the difference will be slightly greater than 0.5. So I actually consider this polar. If you look at just the Lewis structure, it's not going to help a ton to understand, but there's going to be a dipole towards the chlorine. It's a little bit more electronegative. And for the sake of this question, we're going to say it's polar. But if they have one like this for some reason, I would just double check with the electronegativity chart they give you and look at the differences to make sure it's greater than 0.5 to consider it a polar molecule. So if it's polar, so I wrote polar, but when polar interacts with polar, we call that a dipole-dipole interaction, right? So I'm going to put dip. All right, PF3. Now, you can kind of see that if you hadn't learned Lewis structures and if you hadn't figured out how to figure out what the shape is and whether it's asymmetrical or if it's not become polar or not, you're not going to be able to solve a question involving boiling point or melting point, which are applications of intermolecular forces. So it's really important that you know how to do this stuff. So the Lewis structure for this guy looks like this. Okay, and obviously bound to fluorine, so it's going to have a dipole for sure. And this lone pair is creating an area where it's offsetting, it's not offsetting a vector, and so this becomes polar, and that just becomes dipole-dipole. Okay, SF4. If I draw SF4, what you should get is sulfur in the middle. Okay, it can expand its octet, so it's going to make these 4 bonds. And you'll actually find out that it has 2 lone pairs on the middle. Now, this is one of the few cases where lone pairs actually make the shape symmetrical because if you remember from, let me go ahead and reshape this a little bit. If you remember from the problem we did earlier, the lone pair from this one right here actually made it asymmetrical because there was an axial plane that had a vector that was not offset. And in this case, we have a lone pair on the top, a lone pair on the bottom, and then we have 1 going into the page, 2 going into the page, excuse me, and then 2 coming out of the page, okay? Now, these 2 vectors, what we were saying earlier, right here going across and in and out of the page, these canceled each other, right? And so would these guys, if these dipoles right here. And there are no vectors on the axial plane. There's no dipole going up or down. And so this is actually one of the few cases one of the 2 cases that you should know about, where lone pairs actually make the molecule symmetrical and by default non-polar. And if it's non-polar, then the dominant intermolecular force can only ever be London dispersion. Okay, and so that's going to be the dominant intermolecular force here. So I'm going to put LD. Okay, SF6, last one. Okay, if I put this here. Okay, this is what it looks like, and there are no lone pairs on the central atom. And if you notice, this is it doesn't have, because it doesn't have any lone pairs, it becomes symmetrical. And when it's symmetrical, even if there are dipoles in the bonds, which there are, okay, they all cancel out, and so this is going to be London dispersion as well. All right, so there are 2 ways they could ask this question. They could ask for the dominant intermolecular force or for all the possible intermolecular forces. If it's ionic, you're going to assume just ionic and London dispersion. Dipole-dipole, that's going to be dipole-dipole and London dispersion. Hydrogen bond, that's going to be hydrogen bond, dipole-dipole, and London dispersion. Dipole-dipole is also has London dispersion, and this would just be London dispersion. Okay? One of the concepts or applications of intermolecular forces is something called volatility. Volatility, if you don't know, it has to do with the principle that above any liquid, there is a gaseous form of that same liquid. So if we could measure it, you would see that above any liquid, there's a small, even if it's minuscule, a very small amount of the gaseous phase of that liquid just sitting above it. And volatility has to do with the principle that atoms want to jump up into this gas phase, but if they have strong intermolecular forces pulling them down, right? If they're interacting strongly with one another, they can't jump up very easily. And so only substances that have lower intermolecular forces or weaker intermolecular forces will have higher volatilities, because that means more particles are jumping up into the gas phase. So when you're looking at a problem like this, when they're asking you to compare or label in terms of increasing or decreasing intermolecular forces or volatility, the very first thing I do is determine what the strongest intermolecular force for each substance is first. If they're the same, then I look at size. But first, let's look at the strongest IM force. So in letter A says CCl4, CF4, and CH4. CCl4, that's a perfect tetrahedron. It has no lone pairs, and that means that all the vectors of dipoles, which there are between carbon and chlorine, all cancel out. And so this is just going to be a nonpolar molecule, which means London dispersion is the strongest intermolecular force there. And you'll actually notice that that's going to be the exact same for the rest of these, okay? So now that they're the exact same, the only thing that's going to differ between these is their size. And their size is important because the bigger the molecule, let's say I've got a molecule here and a molecule like this, the bigger the electron cloud surrounding the molecule, the more easily it's manipulated or repelled back, which creates the London dispersion force a lot easier than if you have a smaller electron cloud. So in other words, bigger substances will always have stronger intermolecular forces due to London dispersion forces than smaller ones. So if I look at this, increasing volatility is actually decreasing IM forces, right? So I'm actually going to label these. If I have, here's the less than sign. I'm going to put these in terms of decreasing IM forces so that I can put it in terms so that it matches the increasing volatility. So I would expect that CH4 has the highest volatility because it has the weakest intermolecular forces because it is the smallest of the three, right? It's the smallest of the three. Hydrogen is smaller than fluorine and chlorine. Then I would expect probably CF4 and then CCl4 at the end here. So on the test, they'll likely use these signs, less than signs, rather than commas and just having you label them, just because it makes it clear. But a lot of students will actually mix this up. They'll actually think of this correctly, but they'll put it backwards. They'll actually put the CH4 here and the CCl4 here. Don't do that, okay? Just be wary that this is a less than sign. And when we're talking about increasing volatility, we're talking about decreasing intermolecular forces. So, all right, so B says propane, water, propanol, and methane. Back when Chem 105 had organic nomenclature, you would probably know what propane and propanol and methane are. But because they no longer have students memorize organic nomenclature, I'm just going to tell you what these are. So propane, hopefully you know the stick version at least. That's propane. Propanol would look like this. Whoops. Look like this. Okay. Methane is just CH4. Okay. And then obviously, hopefully you know water. Okay, so those are the four that we're comparing. Now, I'm going to label the most dominant intermolecular force on each one. This is a nonpolar molecule because it's just carbons and hydrogens. This is hydrogen bonding. This is also hydrogen bonding. And this over here is a London dispersion. Okay, so now in terms of increasing volatility, let me use the greater than and less than sign again. Now I've got four substances because I'm going to have three of these less than signs. I'm going to look at the weakest intermolecular force first. And so I'm going to compare London dispersion with London dispersion. Okay, CH4 is clearly smaller than propane. Because remember, propane, this is CH3 over here, CH2, and then CH3. Okay, that's propane. But this is just CH4. So it has a smaller electron cloud, which means it has weaker London dispersion forces, which means it has the highest volatility. And then by default, because it's the next London dispersion force, I'm going to assume that it's going to be propane. I'll just put propane. Oops, we got propanol, so I'm not going to make it too confusing. So propane there, because it doesn't have anything else. It's just got the hydrocarbons there. Now, between water and propanol, so they both have hydrogen bonds, but this is where students might get confused because with water, the reason it's so good at hydrogen bonding is because it actually has 4 sites of hydrogen bonding. It's got one right here, it's got one right here, and one right here, and one right there. Okay, and that allows it to hydrogen bond on all sides of itself. And that is not possible with propanol. Propanol has like this tail that it kind of impedes it from being able to hydrogen bond well. That's where I've drawn the hydrogen here. That's actually where it's at in 3D. And so it only has 1, 2, 3 spots. And even though it has those 3 spots, it's not able to always interact with another OH on another propanol because it's got this huge tail hindering it. Okay, so water is actually going to have the lowest volatility because it has the best ability to hydrogen bond and the highest intermolecular forces, and then propanol would come next. Okay, so that's kind of how you want to think about these problems. We'll do one more. I'll pause it first. I'll pause for a second so you can try C on your own if you haven't tried it already. Okay, so letter C, NH3, CH4, and SiH4. Let me go ahead and erase these really quick so we can have some room. If we're figuring out that most dominant intermolecular force, NH3, that is H bound to an N, which can then bind to another N on another NH3. So that is a hydrogen bond. That's a hydrogen bond. CH4, we've dealt with that in the previous two. We know that's London dispersion. And SiH4, Si is right below carbon. It makes 4 bonds just like carbon does. And so it's going to have the same shape, but it's going to be just a little bit bigger, but it is just going to be a London dispersion. So when we're comparing these, I'm going to expect that ammonia here, NH3, is going to be at the bottom, is going to be the lowest because it has the highest intermolecular forces. So it's going to have the lowest volatility. Then between silicon H4 and carbon H4, silicon is bigger, and so it's going to create that bigger electron cloud, makes it more polarizable, and that means I'm going to put, whoops, not LD, I'm going to put SiH4 here, and then CH4, all right? So that's kind of an example of a type of ranking question in terms of intermolecular forces that they may give you. Now, on the opposite end of this is surface tension, boiling point, melting point. These are all opposite of volatility in that they increase, they have a direct relationship with intermolecular forces rather than an inverse, meaning the higher the intermolecular force, the greater the surface tension, the greater the boiling point, and the greater the melting point, okay? So in this case, I'm just going to go through this one pretty quick because I feel like it's a reiteration of what we covered already, and it's pretty straightforward. Letter A says heptane or nonane. Heptane is just C7, H16, and this is nonane would be C9, H20, okay? In this case, this is bigger, and so it's going to have more intermolecular forces. Otherwise, these would just be both be London dispersion, but this has a longer carbon chain and more hydrogens, and so it's bigger, and this would have stronger London dispersion forces, and thus stronger or greater surface tension, boiling point, and melting point. Water versus isopropanol. We talked about water here, and then isopropanol looks like this. Okay. Again, back to that example of hydrogen bonding. This only has 2 or 3 sites of hydrogen bonding on it, whereas water has 4 sites of hydrogen bonding. It's got one right here, one right here, one right there, and one right there. Okay. And so, and the isopropanol doesn't have, it has this tail, this big back to it that's preventing it from hydrogen bonding well. It has to be in the right position to do it, and so it's not always favorable, and so this is kind of hindering it. So I would expect water to have a higher surface tension, boiling point, and melting point because it has not only the hydrogen bond, but it's able to hydrogen bond better than isopropanol can. All right, ethane versus ethanol. Ethane just looks like this. Whoops, actually it doesn't look like that. It was propane. Ethane is just C to C, and then this is H3 and H3. The only difference is that ethanol has an OH group. If you haven't noticed, anything that ends with all has an alcohol group on it, which is just OH. Okay, so this OH obviously makes a difference, right? And if I were to label the strongest intermolecular force on each one, this would be London dispersion, and this would be a hydrogen bond, right? So I'd expect this one just by default, knowing that it's got a hydrogen bond, to have a higher intermolecular force. Now, this one's going to, I don't know if I even want to cover this one, but just in case anybody's curious, this one's between PVC or dodecane. Dodecane is C12, H26. PVC is polyvinyl chloride. Polyvinyl chloride, you've probably heard of PVC pipe, right? That is really tough stuff. And the reason is because it's like thousands of carbon chains long. It actually has chlorines coming off as well. That's why it's called polyvinyl chloride. It's got several thousands of carbon chain long substances with chlorines coming off the end, and they're all nonpolar, and these become very strong. So another thing we haven't noted yet is that London dispersion forces can actually be extremely strong, stronger than even ionic forces when the chains are very big or the molecules are very big. So PVC pipe is actually just made of crazy long carbon chain molecules that just London dispersion use London dispersion forces very well to interact with one another. So that's why it's really tough. Things like gasoline, it also uses London dispersion forces, and it's relatively, it has relatively strong intermolecular forces, but you can burn it pretty well, or you can, it has a higher volatility than normal, right? So dodecane, even though it's, a 12 carbon chain long, chain, polyvinyl chloride is like thousands of carbons long, and so it's going to be a lot bigger, and so I'm going to put PVC. Like I said, they're probably not going to test you on something like that, but just to kind of reiterate the principle of London dispersion forces, I wanted to include that one in there. Okay, last kind of idea on these. Well, we have one more question on dissolution, which will kind of use intermolecular forces, but this is the last type of straight intermolecular forces they may ask you, where it's identify all forces present. Now, I've done this a little bit in the previous problems that we've covered in this review. I just want to reiterate: water, it's going to be hydrogen bonding, but it's also going to have dipole-dipole. And then London dispersion, because everything has London dispersion. Same thing for isopropanol. PF5, if you were to draw it, it's actually nonpolar, so it's just London dispersion. PF3, though, if you were to draw that, it's asymmetrical, and so it ends up being London dispersion and dipole-dipole. So just all I wanted with this question was for you to recognize that intermolecular forces can all be there at the same time, but there's always going to be a dominant one that controls the intermolecular force more than the other ones. Okay. Now, dissolution kind of also involves this when we're looking at what dissolves what. Water is a very polar substance, so polar substances are going to dissolve other polar substances, whereas nonpolar substances, I'm just going to put NPO for nonpolar, will dissolve nonpolar substances. So as long as you know what is polar and what's not, you'll be able to decide which one dissolves best in what substance. So propane is nonpolar, so I'm going to say octane. Isopropanol is polar, right? It's got that alcohol group, and so it's polar. It's going to interact with water best, so I'm going to put H2O. BRF5, we learned earlier in a problem that it's polar, and so it's going to interact with water. That's going to be just water. Yep. Same thing here, H2O. We said this one was polar earlier, also polar, non-polar here, though. So this would be octane, and this would be octane as well. And so I recognize that I went through this fast, but it's just based off the stuff we've just been covering. So as long as you know that polar substances like water will only dissolve other polar substances, or nonpolar substances will only dissolve other nonpolar substances, if you can just identify which ones are polar or nonpolar, you have this question really easy. Another dissolution question they may ask you has to do with ions dissolving in water, or things like or any polar solution. So when they say aqueous, that's just water, okay? And water's polar. So now we're talking about an intermolecular force called an ion dipole intermolecular force. And they're going to ask you which one's going to experience the strongest ion dipole interactions. Now, the way that you do that is based off a principle called Coulomb's law, where it's proportional to the charge of one times the charge of the other over the distance between them. Now, this equation is relatively is a little bit more complicated. It has a K constant in it and stuff. I'm not going to focus on that. Let's just focus on the charges here. So in this case, we have the charge of 1. Let's say that's -1 and a +1, right? If an anion, let's say Na plus, was getting close to a Cl minus, okay, that's a negative charge on one times the +1 charge on the other. Over the distance between them, that would just depend on the size of these, where they are on the periodic table. So the distance is inversely related to the force. Does that make sense? If it's closer to one another, then they're going to have stronger forces. If they're farther away from each other, they're going to have weaker forces. So for these kinds of questions, note that the magnitude of any charge will take precedence, meaning it will affect the intermolecular forces more than the distance will. So focus on those first is my suggestion. So I'm going to put them into two categories. I'm going to put them into the 1+ category, okay, Na plus and K plus, and then I'm going to put them into the 2+ category, knowing that those in the 2+ category are going to have the stronger intermolecular forces. So if I'm doing these greater than or less than, or greater, or the less than signs, I know that the 2+ are both going to be here and here, okay? So I just have to determine which one is the strongest first. Now, if I look at magnesium, magnesium is above calcium on the periodic table, which means it is smaller. It goes opposite of the electronegativity, electron affinity, and ionization energy periodic trends in the periodic table. And so magnesium is smaller, and therefore the distance between magnesium and the water molecules that it's interacting with is smaller, which creates a stronger ion dipole interaction. And by default, I'd put calcium here. Same idea here between sodium and potassium. Sodium is smaller, so I'd expect it to have a stronger intermolecular force with water than the potassium, which would have the weakest. Okay, does that make sense? All I'm doing is I'm applying this Coulomb's law equation to this idea of ion dipole interaction. So I've got the charge of 1, which I said, let's just say water is an arbitrary plus or -1, right? We'll say it's an arbitrary -1. Each of these will either have a +1 or a +2. Okay, and that is going to affect the force first, primarily than the distance will. Once I've determined that two have the same charge, then I look at the distance, and we've determined that because the smaller one is makes it closer to one another, the smaller distance creates a closer proximity, then they're going to have a stronger ion dipole interaction, and then I just rank them accordingly. Okay. Okay, now on to phase diagrams. Phase diagrams explain based off of pressure and temperature what phase, either solid, liquid, or gas, a particular substance will be at. So it says, explain why you might never see this compound as a liquid in everyday life. Well, if you look at where it is a liquid at the temperature and the pressure at which it's at, you'd have to be at an atmospheric pressure of 5.1 at least, and at least this would be the triple point, right? But even to be passed into this range, that's the minimum where you'd have to be. And this is not only incredibly cold, but this is a really high pressure. And we don't really live, as humans, we don't really live anywhere above or too much above or too much below 1 atmosphere. We're kind of in the range between like 0.9 and 1.1. And that's really about all, but most places, that's about the range. They may be a little bit more or less than that of where humans live. And so just based off the pressure, we're not going to probably see this in everyday life. Now, there's a rhetorical question where it's like, do you know of a substance like this? Really, there aren't many that maybe will come to mind, but if you ever heard of dry ice is like this. It's a solid, and when you bring it to a high enough temperature, it turns directly into a gas. It sublimes is what we call it. And this is a common everyday example, if you make homemade root beer or use dry ice for, any other purpose. That's pretty much what this is. It's a common everyday thing. It's just CO2. That's just dried CO2. That's just dry ice. And you'd have to have it at this pressure, or at this, you'd probably have it around 1 atmosphere. And then once you get into the, this range of regular temperature, human temperature, that's probably where it'll start, where you'll probably start to notice it subliming. And then we store it in really cold temperatures, like way down here. Okay, so where are the sublimation deposition points? Okay, sublimation and deposition, subliming, which is what I just mentioned. Subliming is going directly from solid to gas, okay? And deposition is the exact opposite. So deposition is gas deposing into a solid. And so the line that connects these is this line. It's called, in this case, it's the B line. Okay, that is the sublimation deposition point. And then where the melting freezing points, melting and freezing would be between a solid and a liquid. So this is that line right there. And then if you were doing evaporation or condensation, that's where you would put this line, okay? So pretty basic, I think, as long as you can understand that this is the temperature scale, that's the pressure scale, and that from left to right would be a solid, liquid, and then a gas. All right, one thing to note with this phase diagram is that it differs from other phase diagrams in that the slope between the solid and the liquid is a little different. Let me show you. In this one that we just did, this one right here, this has what we call a positive slope, meaning it's increasing in this direction, okay? Even though it's slight, it's only by a little bit in the x direction, but it's by a ton in the y direction, right? But it's important to note that it's a positive slope because think of it, if you were to increase, if you were to stay at the same temperature, let's say we're at this temperature right here, okay? And we were to maintain this temperature, if you go up, if you go up on this graph, you notice that as the pressure increases, it's going to become more often a solid, okay? That's because putting pressure on will cause the substance to take on the most dense form. And in most cases, the most dense form is a solid. But in this phase diagram, when you see this negative slope, okay, this negative slope means that it's more dense as a liquid than it is a solid, because if you were to take the same temperature and increase it in the y direction, you'll notice that it turns into a liquid before it go, more often than it does a solid. And that's because the liquid form of this substance in particular is more dense than its solid form. So this is the phase diagram for water. Water is one of the unique substances that will actually have a less denser form as a solid than it does as a liquid. This is why ice floats. If ice was more dense than its liquid form, water, it would actually sink. And this is what happens most of the time. But water is unique. Water has special angles of hydrogen bonding that allow it to make really cool hexagonal structures. It'll actually make this particular hexagonal structure where it'll interact with other hydrogen bonds in water. Okay, and it forms these like hexagonal structures. You'll see this, this. Okay, and this packing creates these pockets of air. And these pockets of air in the frozen form of water will make this less dense. Okay, it's less packed in. And the only way to pack these in is if you liquefy it. Okay, and so that's why the solid form of water, ice, is less dense than its liquid form, water. So what is this substance likely to be? We answered that. That's water. So anytime you have a negative slope, the key here is that what that means is that the solid form is less dense than its liquid form. If you were to take it at this, a constant temperature and increase the pressure, okay, it turns into a liquid because the liquid, this is liquid, this is solid, and this is a gas. Okay, it turns into a liquid because it's more dense than its solid form. All right, so on to stoichiometry. Ammonia reacts with sulfuric acid to produce ammonium sulfate. If you wanted to produce 85 grams of ammonium sulfate, and you knew that there was a 72% yield exactly, how much ammonia would you need to react with excess sulfuric acid? So the very first thing I would do is write and balance a chemical equation. So in this case, hopefully you know that ammonia is NH3. Okay, you don't need to know the phases in this class. That's more focused on in Chem 106. So I'm just going to put, hopefully you know what sulfuric acid is though, right? If you remember what sulfuric, remember adic and itis, this is an ic, so we must have been at sulfate, which is SO4, and that's a 2- charge. And if it's an acid, that means it combined with H+, so when we switch this superscripts, it becomes H2SO4. And acids are always in an aqueous solution. Okay, and then I yield, what do I produce? I produce ammonium sulfate. Ammonium, if you remember, it was one of the polyatomic ions you had to memorize, which is NH4+. Okay, and then we had sulfate. Sulfate was SO4 2-, right? So now I'm combining SO4 2- with NH4+. So in this case, I'm going to get, when I switch the superscripts here, I'm going to get NH4 in parentheses because this is there's two of them, and then SO4. And that would be my chemical equation, my unbalanced chemical equation, but my chemical equation. So now let's balance it. Let's start with the nitrogens. Okay, so in this case, I've got 2 nitrogens on one side, or 1 nitrogen on the reactant side, and 2 on the other, right? Whoops, I've got a 2 right here. There's 2 nitrogens here. So let's just put a 2 in front of this guy. And now let's figure out hydrogens. First, I've got 6 here and 2 here. So it's going to be a total of 8 hydrogens over here. And 4 times 8, yep, that's 8 hydrogens. So we're actually good on hydrogens. And we've got 1 sulfur, and 4 oxygens and 4 oxygens. So we're actually good. We don't need to balance this any further. So just having the 2 coefficient in front of the ammonia is totally balanced. So that's the very first thing that you want to do. Now, the second thing you want to do is identify the limiting reactant, okay? That is going to be the value of which we use to solve for certain things in a reaction. If we ever used we would only use the excess reactant if we were looking for leftover excess reactant or how much of it was used, because it's not super useful in telling us how much product we formed or anything about the percent yield. Okay, so if you wanted to produce 85 grams of your product, ammonium sulfate, and you knew that there was a 72% yield, how much ammonia would you need to react with excess sulfuric acid? Now, some students might start with this 85 grams and just start using a mole-to-mole ratio between ammonium sulfate and, let's say, this is going to be 1 mole of ammonium sulfate per 2 moles of ammonia, and then just go from moles to grams. That is incorrect. This is incorrect. We don't do that. The reason is because this is not a theoretical value. We only plug in values into this dimensional analysis if they are theoretical values or if they're values that were given to us and we're solving for a theoretical value, okay? So what they've given us is what we actually want to produce, right? This is the actual yield. That's what we actually want. If you remember, percent yield is equal to actual over theoretical times 100, right? Times 100. What they've given us in this case is the percent yield, okay? But they've given us the actual. And we have to solve for the theoretical in order to plug that into all those equations so that I can figure out not only how much ammonia I would need, but the amount of ammonia I would need to produce exactly 85 grams of ammonium sulfate, okay? Knowing that there's a 72% yield. So I'm just going to say 0.72 is equal to actual over theoretical, okay? And then I'm going to say this actual here is 85, right? 85. So in reality, it's going to be 85 divided by 0.72. If you do that, you get about 118.06 grams of what? Of ammonium sulfate is the theoretical yield, okay? The theoretical yield, given that the percent yield was 72%. So this is the value I want to use when I'm figuring out how much ammonia I need to produce 85 grams, because I'm not going to 100% completion. If I went to 100% completion, I'd get 118. But because it's a 72% yield, that's 85 grams that I'm producing, and I'm going to figure out how much ammonia I would need, given the percent yield, to do that. So when I'm setting up the dimensional analysis, I'm going to put 118 in the beginning, 118.06 grams of ammonium sulfate, or not, of ammonium sulfate. Okay, times, and then you put the molar mass of ammonium sulfate down here. So I'm just going to hold that off for a second. 1 mole of ammonium sulfate times, and then you're going to use a mole to mole ratio between ammonium, so mole of ammonia between mole of ammonium sulfate. Okay, and this is just a 1, okay, to 2 ratio, so 1 to 2 mole ratio. That's why we need a balanced chemical equation, because if we didn't, then we would actually get a value that is not that doesn't match the correct ratios of everything together. So just be wary of that when as far as like why we do balanced chemical equations. Then we just turn this into grams. Okay, so I actually have it all written out here, the work here. So here we have the balanced chemical equation. We have the 2 in the front there, and then we got the actual over theoretical. We solve for the theoretical. Okay. And then we just plug this into the mass. So here's the molar mass of ammonium sulfate. Okay, and I know that the molar ratio between ammonium sulfate and ammonia is 2 to 1. And then here's the molar mass to ammonia. This is exactly how much ammonia I would need to produce 85 grams, not 118, but we had to use the 118 as a theoretical to solve for the amount of ammonia we would need to get the actual yield of 85 grams. Okay? Does that make sense? So there are multiple ways they can ask you about this. This is one way. I think this is the more complicated way compared to the other questions that we'll cover those other types of questions as well. But I feel like this one confused the students a lot, and I just want to make sure that you don't get confused when you see the actual as what you're trying to is what they give you to solve for how much of a reactant you'd get. Okay, so that's the work for it if you want to look over it again. Another stoichiometry equation. It says, write a balanced chemical equation for the combustion of hexane. Okay, so you should know stoichiometry, it refers to the relationship between the amount of reactants that you have and then the products, both before and during and following chemical reactions. And a lot of people, when they think of stoichiometry, they think immediately of balancing chemical equations, and that's really all it is. So in this case, they're asking us, write a balanced chemical equation for the combustion of hexane. Hexane, they used to make you know what that is in Chem 105, but I'll just give it to you. So it's C6H14. Okay, and the combustion, hopefully you do know this, combustion is where we burn it, and flames require oxygen, so we burn it with oxygen, and it produces carbon dioxide and water. That is a combustion reaction. Typically, it's going to be a hydrocarbon that we blow up, and it produces carbon dioxide and water because we have a carbon and a hydrogen that will react to produce different compounds with oxygen. Okay, so in order to balance this, it can get kind of confusing depending on how much experience you have with this. If you have a lot of experience, it's probably going to be easy, but I'm going to run through a quick way of how to balance a chemical equation. First of all, just keep track of how many you have on each side before you start balancing. Okay, so on this side, I got 1, a 2, and then 3 over here. Okay, so the very first thing is to balance the elements that are in one element on each side, or one product or reactant on each side. Meaning, since there's only 1 carbon here and 1 carbon here, it's really easy to balance. So I'm going to start balancing by balancing those. If I put a 6 in front of this, I end up getting 6 carbons over here. But now I have to change my amount of oxygens because that has also changed. So now that is going to be, let's see, 12 plus that's 13. Okay. Next one, let's try hydrogen, since that's also in just one of them on each side. Whoops, right there. Okay, so let's, if we do that, I'm going to say, let's put a 7 right here, and that would create, whoops, wrong number, 14 over here. And that balances our hydrogens. Now, that changed my oxygen count to, let's see, 19. Okay, 19. That's kind of a funky number to have to deal with. So what's nice about this equation is that there's oxygen is only on one side, or one part of the reactants. And so if I wanted to get to a 19 on from this side to this side, you can really just take this number and divide it by this number and put it as the coefficient, so 19 over 2. And then if you do that, you can't obviously leave a fraction as a coefficient, but if you multiply the whole equation by 2, meaning all of this by 2, not squared, sorry, just times 2, okay, you end up getting the following. You'd end up getting 2 in the front here, 19 here. It's 12 and 14 respectively, okay? And then if you were to count these, we can double check just to be sure, but the carbons here, we end up having 12 on each side, 12 and 12. Hydrogens, let's see, we've got 28 on this side and 28 on this side, perfect. And then lastly, we can count our oxygens. We've got, let's see, 38 on this side, right? We got 19 times 2 here. And then we've got 24 coming from here, 24 plus 14, yep, that's 38. 38. So now we're all balanced. So it was just that trick with, you know, the 19 over 2 coefficient to put here, only because oxygen was in that one spot. Other than that, it shouldn't be this complicated to balance a chemical equation. And the fact that your test is all multiple choice will help to kind of do deduce what the answer is instead of having to run through this process. But just in case you were kind of sketchy on balancing equations, I wanted to run through this. All right, so now we've balanced it, and they say we have 1 gram of hexane and 1 gram of oxygen, which is the limiting reactant. So now in this case, what we want to do is we have this balanced equation, and when we determine the limiting reactant, we have our 1 gram of hexane here, our 10 grams of oxygen here. And what we're going to do is we're going to convert them to moles first, okay, moles of each. And then compare those to the coefficients that are in front of them, okay? Because those are going to largely determine what how many moles of product I would produce. This is one way to do it. You are also able to go all the way to another product and find out, you know, by how much grams each one is produced. And whichever one produces the least amount of grams or the least amount of moles of product is going to be your limiting reactant. So just because we're only finding the limiting reactant, we don't need to actually find grams or moles of product. I'm just going to use this ratio here. And we find that this 1 gram of hexane is going to be our limiting reactant because it only produces 0.0058 moles times whatever the coefficient of the product would be. So it's going to be the limiting reactant. With excess reactant, they've asked us, okay, so now we know that this is our limiting reactant, but our excess reactant, we can find by actually reacting or using a multiple ratio directly with both reactants. You could technically go to grams of product and go backwards as well, and grams of product to, you know, moles of oxygen used to grams of oxygen used. That's fine too. But I like doing it this way just because I like to relate the reactants together. So I take how many moles of reactant or of the reactant I have, that's my limiting, and then compare it to the excess reactant using a multiple ratio, and then figuring out by grams how much that was, and you get the total minus how much you used. This would be how much we have left. Like I said, there are multiple ways to solve for excess reactant. You could have used the grams of product from the limiting reactant and then plugged it in here and done the same multiple ratio, except a multiple ratio between oxygen and the product instead of this one. But you should always get the same answer. It should come out the same. Your answer should be about 6.47, okay? So they also asked us in the problem, if it actually produced 1.954 grams of carbon dioxide, what is your percent yield? Remember that percent yield is equal to the actual yield, okay, over a theoretical yield, meaning mathematically when we type it out, this is in theory how much we'd produce, but in the real world is not so generous, okay? We usually produce only a fraction of what we actually put in. So what we have to do is they've given us the actual. This is actually how much came out. That's our actual value. And we can find a theoretical, and they're ultimately looking for the percent yield. Technically, this is times 100 as well, if you want to put it into a percentage. Okay, so we can take this, solve for a theoretical, and then put one over the other to find the percent yield. So here, in order to do that, here's our limiting reactant amount, right? This is how many moles we had. This is the 1 gram of hexane that we had turned into moles. And then we did a multiple ratio with one of the products and turned it into grams of product, because this is going to be the theoretical yield of carbon dioxide, okay? That's why we had to use the limiting reactant to find out how much we in theory produce. So then what we do is we take the actual over the theoretical, and we find that that's about a 63.8% yield, okay? All right, on to combustion. Okay, so it says you burn 95.6 milligrams of some hydrocarbon-containing oxygen, and find that you produce 269 milligrams of carbon dioxide and 110 milligrams of H2O. What is the molecular formula given that the molecular weight is 312 grams per mole? All right, so the purpose of combustion is to find out what these subscripts are, what the chemical formula of the hydrocarbon is. So that's the reason we do combustion analyses in the first place. So hopefully that helps understand where we're going. So we know that we have 95.6 milligrams of whatever this is, 269 milligrams of this carbon dioxide, and 110 milligrams of water. Okay, so the reason that this helps is, if you notice in this problem, we only have carbon on one side. On the product side, we only have it in one molecule. And on the reactant side, we only have it on one molecule. So assuming that it goes to 100% completion, which, in theory it wouldn't, but look, for these questions, they don't really say otherwise. So we're going to assume 100% completion of a reaction. All the mass of carbon that's in this carbon dioxide had to have only come from the mass from my hydrocarbon. So if I found out how much carbon was here, I could find out how much carbon was my original sample. The same thing happens for hydrogen. It's only in water here and only in my hydrocarbon here. So I can actually solve for that. It actually is not the case for oxygen, right? Oxygen's actually in all four things, and oxygen could have come from this or my compound. And I don't even know if it has oxygen unless it tells me otherwise, or the total of the carbon and the hydrogen add up to the original amount of my sample. But that's because they told us that there's oxygen, we're going to have to assume there's oxygen. And again, we don't know if the oxygens here came from our sample or from the oxygen we burned it with. So we have to kind of find carbon and hydrogen first, and then take those from the total and see how much by mass is left of oxygen. And I'll show you what that looks like here in a second. So the first thing that we do is we take the mass of oxygen, okay, turn it into moles, and use a mole to mole ratio of not of a product to a reactant, but of a molecule to an atom within the molecule. For every 1 mole of carbon dioxide you have 1 mole of carbon and 2 moles of oxygen. Okay, if it was water, for every 1 mole of water you have 2 moles of hydrogen and 1 mole of oxygen. Okay, so this is just a matter of, it's not necessarily a mole to mole ratio per se in terms of stoichiometry. It's a mole to mole ratio in terms of molecules to atoms within the molecule. And I hope that makes sense. We're doing this so that we can isolate the grams of carbon specifically. So when we do this, we convert this to moles, find the mole to mole ratio to carbon, and then turn it into grams of carbon, and this is how much grams of carbon we have. Same thing goes for water here. The first thing we do is you turn it into moles of water, and I know that for every 1 mole of water there are 2 moles of hydrogen. Okay, and when I know that with 2 moles of hydrogen, I know that in 1 mole there's 1.00794 grams. These come from the periodic table, these two values here. Okay, and ultimately that helps me find out how many grams of hydrogen I have. Now, they told me in total I had 95.6 milligrams of my hydrocarbon. So what I could do is I can technically add these up, add both of these up, and take them or subtract them from the original total to find how much was left over in oxygen. And so that's why we do this in the first place. That's why we convert these to grams, so that we can use the mass of the original sample to find out how much oxygen there is. After we do that, we take all of the gram samples of each substance. So here's my grams of carbon, here's my grams of hydrogen, here's my grams of oxygen that I just found, and we convert them each into a mole. Okay, each into a mole. When we do that, we get a certain number for each one, and we divide all of them by the smallest value. A lot of people are confused about why we do this. Let's say, I think I've covered this in a previous problem in this review, but I want to make sure that I get this through. So let's say we have 20 bags, okay? And I have 10 cans of tuna. And I asked you, what is the ratio of bags to cans of tuna? You would say 2 to 1, right? All you did was divide each of these, divide the 20 by 10. But another way that we do this, and it works out the same way, is we divide them by the lowest possible ratio, the lowest possible number. Okay, and that equals 1, and this equals 2, and that's still a 2 to 1 ratio. So I would say anytime you're comparing numbers and you're comparing a ratio of all of them to each other, you always divide by the lowest number, even if you don't realize that you do that. And so here what we do is we find moles first. We can't do this with grams. We find moles first, and then we find the one that's the smallest. In this case, it was oxygen. We divide all of them by the smallest value. And we find that we get approximately 10, approximately 20, and approximately, well, this would be exactly 1, right? It's divided by itself. Sometimes you might get something like 9.98, right? That's close enough to 10. If you're getting something like 9.32, that's a little too ambiguous. It's going to be a little bit more obvious. I would say within about 0.1 of the rounded value is where you should be. Okay, so if it's like 9.9, I think that's fine. But if it gets to like 9.7, I would be kind of wary of that, for example, okay? So 10, 20, and 1. Now, what does that tell us? That means there's 10 carbons, 20 hydrogens, and 1 oxygen in ratio to one another. So that gives us our empirical formula. So it's C10H20 or O is our empirical formula. And they've given us a molecular weight, okay, this 312 grams per mole, which is the molecular weight, meaning it's the weight of the molecular formula, not the empirical formula. So what we can do is we can find the molecular weight of the empirical formula, okay, which is 156 grams per mole, and we divide the molecular weight by the empirical weight, and then use this ratio to multiply all the subscripts by that number. In that case, this is where we get our molecular formula. It's going to be C20H40O2. So if this had been, let's say they had told us that the molecular weight was 156, well, then it would just be 1, and this could function both as the empirical and the molecular formula. It's the lowest possible reduced ratio between all the subscripts, but because it's the molecular weight, we could technically say that it was the molecular weight as well, the molecular formula as well. But in this case, obviously they give us a different number, and so we used a different multiplication factor. So all I'm saying with that is that just recognize that the empirical formula could technically be the molecular formula if the molecular formula's weight matches the empirical formula's weight as well, okay? I hope this was helpful in determining and using a combustion analysis to find both an empirical formula and molecular formulas for these types of analyses. All right, on to heat. So with heat, determining whether something is endothermic or exothermic, endo refers to into, okay, and exo refers to leaving or exiting, right? And what that means is we're determining whether heat is going into or out of a system. That's what we mean by thermic. Therm is heat. So endo or exothermic means is heat going into or out of a system. Now, a system is whatever we're referring to as like the main object, and everything else, this would be the system, and everything else is the surroundings, okay? So when water freezes, if water is going to be our system, is heat going into or out of the system? Well, you have to lose heat in order to freeze, right? And so this is going to be an exothermic process. Methane combusts anytime you combust something, combusting is blowing up something. Imagine if you were to put your hand next to something that combusted. Would it feel hot or cold to you? If it feels hot, your hands are the surroundings, so that means heat was leaving the system. Okay, and that means this is going to be exothermic. Think of if you were to hold ice in your hand as well. If you had, I don't know, I'm not going to draw a very good hand here, but let's say you had ice in your hand. Okay, why does that feel cold to you? It feels cold to you because the heat is going from your hand. The ice is taking heat from your hand and melting the ice. That's why it feels cold to you. Okay. So when you think of problems like this, if it's hard for you to think if it's endothermic or exothermic, think first, okay, if my hand was next to it, acting as the surroundings, would I feel hot or cold? And if it feels hot, it's going to be an exothermic process because that means heat was leaving the system that you're touching. Or if it's cold, it means heat is going from your hand into the system that you're touching, okay? Muffins bake. Okay, muffins have to be in an oven in order to bake, right? And so that's an endothermic process, right? They have to have heat in order to rise. Yes, it's hot in the oven, but the oven is the surroundings, not the system, right? So the muffins have to have the heat to go enter in order to bake. The reaction from a hot pack. Okay, a hot pack obviously is going to feel hot, and so when you feel it, your hand it's releasing heat, right? And so you feel that heat. That's an exothermic process. Last one, a sodium metal melting. Okay, in order for a metal to melt or anything to melt, really, it has to have more heat go into it, right? So it's going to be an endothermic process. The heat is going into my system. All right, so on heat and work, now we're actually going to put some actual values into these energies. In this case, we're going to be working, dealing with work. Okay, so it says an expanding gas does 145 joules of work on its surroundings at a constant pressure of 1.05 atmospheres. If the gas initially occupied 480 milliliters, what is the final volume of the gas? Okay, so there's an equation that you should know, which is the work is equal to negative P delta V. Okay, P is the external pressure, delta V is V final, minus V initial, so delta volume, and then obviously our work in liter atmospheres. So they give us the work done in joules. So firstly, the very first thing that you should do is turn this into liter atmospheres, because the only number that you should be plugging in here is one that's in terms of liter atmosphere units, not in terms of joules, because otherwise you're going to get a wrong answer. So be wary of that. When you're plugging in for the work equation explicitly and they give you an energy that's in joules, first convert it into liter atmospheres. When you do that, 145 joules, for every 145 joules you have, there are 101.3 joules per 1 liter atmosphere. Okay, if you do that, you get about 1.43 liter atmospheres. Okay, so I'm going to erase this if that's okay. And then 1.43 liter atmospheres is the energy I get, so 1.43. Now, one thing to note, too, that a lot of people will miss, they will totally miss this. This is very important. If it's an expanding gas, is this number positive or negative? When a gas does work on its surroundings, it loses its energy, the internal energy, to its surroundings. And so this is actually a negative 1.43 liter atmospheres that it lost when it expanded. Okay, so that's going to be equal to negative P delta V. And in this case, they told us P was 1.05 atmospheres. Okay, atmospheres. And then the delta volume, I don't know V final, but I do know V initial, which is 0.48 liters. Okay, so the very first thing we got to do is divide the negative 1.05 atmospheres over. When we do that, negative 1.05 atmospheres, that way my negatives cancel and my atmospheres cancel. I get about 1.36, and this would now be liters, is equal to V final minus 0.48 liters. And then obviously at this point, it's just add 0.48 over. Okay, so the biggest thing with this one, ultimately you get about 1.84 liters as the V final. Okay, so it expanded. It makes sense that it expanded to this because it's bigger than this. The biggest thing here was knowing that this number here was negative and it had to be in liter atmospheres. Okay, that was really the biggest thing. For the most part, as long as you knew the equation, it's really easy to just plug and chug. But there's a problem on the test, at least there was in the past, that dealt with this, and people would forget either to put this into liter atmospheres or to put a negative sign, and they would have missed this problem. All right, now they're going to start incorporating both heat and work into determining internal energy. Internal energy is the sum total of potential and kinetic energies within a system. Okay, so potential / kinetic energies in a system. I'm just going to put E's. Okay, that is equal to Q plus W. This is heat energy and work energy, where work is equal to, remember, negative P delta V when work is done by the system. So this is the sum total of all the potential kinetic energy. So for the example in the last problem that we did, when the balloon expanded, right? When it's expanding, it's losing internal energy because it's losing work energy to the surroundings. When it's pushing on it, think of if you keep pushing on something, you start to lose strength, right? Because you kind of wear out. So kind of in that same example, if the gas is pushing on something, the further it pushes out, the more energy it is losing. So on the contrary, if anything is pushing down on the system, it is gaining internal energy in terms of work. With heat, it's really easy to think about because it's whether just if heat goes into it, then that's going to increase the internal energy, or if heat goes out of it, then that's going to decrease the internal energy of the system. So you have to know this equation and hopefully just know all the variables there. The delta E is the internal energy, Q is the heat energy, and then W is the work energy. So it says state whether QW and delta E are, for the system are positive or negative. So a sample of water freezes. Okay, let's think of Q first. Q is the easiest one to think of. That's why I think of it first. And you have to know Q and W in order to determine delta E. So we have to first determine those two. So Q, if water freezes, heat has to leave the sample, right? So that's going to be an exothermic process. Now, in terms of work, when water freezes, water is one of the few things that expands when it freezes, right? Hopefully you remember that. So when it expands, that means delta V is going to be positive. And when work is equal to negative P delta V, if delta V is positive, then work ends up being negative. Okay, so that's going to be negative. And that means by default, a negative plus a negative is going to equal another negative. Okay, not times a negative. Okay, this is not multiplication. A lot of people will think that because they're both negative, they're going to end up positive. Negative plus a negative is like negative minus something else. Okay, so that means delta E is going to be negative as well for letter A. All right, so that's for A. I'm going to erase these now and do it for the same for letter B, okay? Letter B says a student heats up a rigid container of argon gas. All right, so it heats it up. So heat is going into, right? Q is positive. We're putting heat into our system, into a rigid container of argon gas. Okay, rigid container, what does that mean? That means delta V is 0, right? There's no change in volume. It's in a rigid container. It's not changing at all. So work is actually 0 here, and by default, a positive plus 0 is just going to be a positive for the delta E, okay? All right, letter C, a researcher compresses a gas sample and heats it up. Okay, heats it up, obviously that's going to be plus. Okay, but he says he compresses the gas sample. All right, so if he compresses the gas sample, that means when work is equal to negative P delta V is going to be negative because the V final is going to be smaller than the V initial, right? V initial is going to be bigger than the original one because he's compressing it down. It's getting smaller. So that means overall work is positive, and that by default, a positive plus a positive is obviously another positive. All right, last one. A reaction releases heat. Okay, releases heat. That's going to be negative, right? We're releasing heat out of the system and produces several moles of gaseous product. Okay, when we release moles of product, what that means is what we've increased our volume. That's as if delta V was positive. When delta V is positive, remember, that means overall work is going to be negative. So that's going to be negative, and a negative plus a negative is going to be a negative. Okay, hope that makes sense. There may or may not be a question like this on the test, but as long as you can think of each of these as in terms of their signs, it's going to help a lot, even when they throw numbers at you to figure out what the overall answers would be for internal energy, or if they're looking for another variable in the equation. So knowing how to give signs is going to be really helpful, especially when they start throwing numbers into the equation. So now they're asking to calculate delta E for the following conditions, giving certain numerical values. Okay, remember delta E is equal to Q plus W. Now, I'm going to put Q and W here, and I'm going to put the values of each one that we find here. So it says A says some gaseous reactants combine to form a liquid product, releasing 205 kilojoules of heat and causing the surroundings to perform 115 kilojoules of work. Okay, so first let's do Q, releasing 205 kilojoules of heat. Okay, that not only is Q 205 kilojoules, it is negative 205 kilojoules, right? We lost that energy, so that's where the signs come in really helpful. And causing the surroundings to perform 115 kilojoules of work. Okay, so if this is our system and our surroundings are doing work on our system, that means our system is gaining that work energy. So this is going to be a positive 115 kilojoules. Okay, if our system did work on the surroundings, then it would lose that energy to the surroundings. But in this case, our surroundings are doing work on our system, so our system is gaining that energy. So when we add these together, we get about negative 90 kilojoules. Okay, for our delta E. All right, B says 88 grams of dry ice absorbs 13.5 kilojoules of heat. The resulting gas does 2.5 kilojoules of PV work on the surroundings. All right, what's Q? Q is we're absorbing this energy, so it's going to be positive 13.5 kilojoules. And then W, in this case, they give it to us in kilojoules. Again, we don't have to convert from liter atmospheres to joules. That's kind of nice. The resulting gas does 2.5 kilojoules of PV work on the surroundings. So are we gaining or losing that? We're actually losing that, right? So that's going to be negative 2.5 kilojoules. That ultimately gets us about positive 11 kilojoules as our delta E. Okay. All right, letter C says a sample of gas releases 3 kilojoules of heat into the surroundings and performs 790 joules of PV work. So in terms of heat, we are releasing this heat, right? We're losing that. So that's going to be negative 3,000 joules. I'm just going to put it in joules because the other one's in joules. And the surroundings perform 790 joules of PV work on our gas. Well, in this case, our gas is gaining that, right? It's going to be positive 790 joules. So that is going to give us a total of about I'm going to put it in kilojoules, negative 2.21 kilojoules. Okay. All right, last one. Letter D says a reaction releases 150 kilojoules of heat and releases enough gaseous product to do 120 liter atmospheres of work. Okay, so now we're in liter atmospheres. We have to make sure that they're in joules so that we get the right unit of value at the end. So in this case, releases 150 kilojoules of heat. So that's going to be a negative 150 kilojoules, right? We're releasing that heat out into the surroundings and releases enough gaseous product to do 120 liter atmospheres of work. So not only are we releasing heat, but we are losing that to the surroundings. So in this case, first I got to turn this into kilojoules. So this is going to be 120 liter atmospheres, okay, times 101.3 joules per 1 liter atmosphere. If you do that, you end up getting about 12.16 kilojoules, okay? I'm keeping it in kilojoules just because we got one in here in kilojoules as well. Now this is going to be negative 12.16 kilojoules, right? Because we are releasing that. We're doing work on, when we release that gaseous product, it's doing work on the surroundings. And so when we add this up, we get about a total of negative 162.16 kilojoules, more or less, okay? All right, in this next problem, we're going to be reviewing principles that we've done in combustion analysis and other things to find an empirical and molecular formula, okay? So it says a particular hydrocarbon has the following percent compositions: 73.783% carbon, 13.9, all that percent of hydrogen, and that percent of oxygen, okay? Determine the molecular formula given that the molar mass is 260.46 grams per mole. Again, this is kind of a review, but remember, we find the mass of the substance, so mass of each one of them, and we convert each percentage into a mass, right? This was 73.78%, and this was 13.93%. It's easiest to do that because we're assuming that we have 100 grams of this sample. So that's why we do this. So assuming there's 100 grams, we would know that 73.783 grams of carbon were there. So we turn those all into their respective moles and then divide by the lowest mole. So in this case, obviously, oxygen is going to be the lowest. So our ratios are about 8, 18, and 1 to each other. They told us that here's the weight of our empirical formula, right? This is our empirical formula. And they told us the weight of the original, it's going to be exactly twice that. So we multiply each subscript by 2, and that's where we get this. This was kind of a review again, but just to make sure that if they ever give you a question on strictly percent composition, this is how you'd go about solving that. All right, last question on this review will have to do with the gas analysis. So they may give you a question like the following. 32.27 grams of an unknown gas occupies 9.8362 liters at 35 degrees Celsius and 752 torr. Further studies indicate that this gas is monatomic. Which element do you suspect that this gas is? So in order to determine what kind of element it is, right, you would have to have a molar mass, okay, a grams per mole. Now, they give you grams, but that's of the unknown substance. But they do give you these other values that if you were to plug into something like the ideal gas law, okay, you could figure out how many moles there are, and given the number of grams you have, you could take the grams and divide it by the number of moles, find a molar mass, and see what element is closest to that. Now, remember that this is a gas at room temperature, so you'd have to make sure that you're on further right on the periodic table. And it's monatomic, so it's likely going to be a noble gas. That's just what we'll expect it to be. So, first thing is you use the ideal gas law, solve for moles, okay? Now, recognize that you have to have everything in the right units because our R constant is in terms of specific units. It's in liter atmospheres per mole Kelvin. Okay, so you have to have a volume that's in liters, a pressure that's in atmospheres, and your temperature in Kelvin. So that's here. What I've done is I've taken the torr and I've divided by 760 because that is the conversion of torr to atmosphere. 760 torr to 1 atmosphere. Okay, and so that's all I've done there is put this into atmospheres. And then we've got the value that they gave us just as the volume in and of itself. Here's the R constant that we have, and then we converted the 35 degrees Celsius into Kelvin, and then we solve for our moles here. Now, they gave us the mass of the sample, and if we know how many moles were there, all you have to do is divide the grams by the moles, and you get this number, 83.8 grams per mole. And if you look in the periodic table, that's most closely aligned with krypton. So that's how you kind of go about a gas analysis on a problem like this. All right, so that's going to finish it up for this problem, or for this exam review. I hope it was helpful. I hope you're able to kind of review concepts, kind of see where you were wrong in your thinking processes, because that's the most valuable thing to do before a test. Additionally, my 3 suggestions are always the same, mostly because whenever I TA'd and I gave these 3 suggestions, I almost always had a student that came up with 100% in my section. So I feel pretty confident with these. Not necessarily that everybody's going to get 100%, but I think as long as everybody does these principles in general, I think you do very well. I'd be very well prepared for the test. So my first tip is to review all the problem sets. Remember, don't just like go through them and say like, oh yeah, I know that. Oh yeah, I know that. And I mean like go through them, cover up your answer, and be able to explain to yourself why the answer is what the answer is, or even if there's math, you don't have to do the math in your head. Just be able to set up the problem in your head, type of thing, or know how to answer the problem. So the problem sets are pretty good gauges, I think. Obviously, the tests are a little bit harder as far as the caliber of the questions, but the problem sets really help teach you the principle. So I highly recommend reviewing all the problem sets. Number 2, go to a TA review, or you can just practice this one. Go through this one, pause the video, practice a question on your own. But a T review, especially one that's specific to you and your class, is most valuable because your TA has likely talked to the professor about what to review, or has even seen the test and knows kind of how to help you or what to review. So those can be very valuable. So I'd highly recommend going to a T review. And number 3, take a practice exam. And by practice exam, I mean taking an exam, the practice exam that they give you in class, seriously. Like, take it like a real test. Go isolate yourself, pretend you're in the testing center and take the test, and then grade yourself and then gauge where you are with certain understandings of the concepts in Chem 105. So that's what I recommend for studying for the tests. There are other resources I think can be helpful, like SmartWorks or reading the textbook. I didn't personally use those, but I know of students who did, and they found them helpful as well. So there can be a lot of other things, but these 3 I feel really confident in, and so that's why I provide them to you. I wish you the best of luck on the exam 3.